So let's go to some applications of this definite integral now. So the first thing will be a finance application, in particular a so-called continuous time finance application. And continuous time finance basically says, well, instead of measuring financial flows as things which happen on a number of isolated times, we are going to look at financial flows as occurring all the time. So every second there might be a flow of money. And sometimes this is a very good approximation. So in modern capital markets, actually there is money flowing more or less all the time. Trades are carried out every second or every millisecond actually. And sometimes this is just a convenient approximation to perhaps more discrete transactions which happen a lot, but perhaps not every second. In particular, continuous time finance is used a lot if you want to do a derivative pricing, because derivative pricing is a lot easier in continuous time than in discrete time. Let's have a look at what that basically means then. So let's look at the following example. So suppose we have some cash flow. So suppose this cash flow is a number of euros that I get every day. T euro per day, where T measures the day, the number of the day if you wish. So I might get, on day 1 I might get 100 euros, and on day 2 I might get 105 euros, and on day 3 110 euros, etc. Then my question might be, well, how much will I have after 100 days, or perhaps after 1,000 days? So that's not so difficult in the sense that if I know what I get on every day, I can just add this up, right? I can do this in Excel if I have all these various numbers. But sometimes it's actually, I have the CT will be given in terms of a formula. In particular, again, if we look at derivative pricing, typically we have some formula that's going to measure how large cash flows will be per day or per second. And we want to add up lots of different expressions involving this particular formula. That will be quite a task because you will have lots, like if you have 1,000 days, you would have to add up 1,000 different terms. So the question is, can we do this a little bit more easily? And the idea is, yeah, we can do so by integrating. Because, well, let's have a look at this particular graph. So basically, suppose each of these bars here, these vertical bars, represent one day, right? So first day I get 100 euro, the second day I get 105 euro, the third day I get 110 euro, what you wish. And here you see the amount is nicely growing day by day. So how much do I get in total? Well, it's precisely the area of all these bars added up. So I would like to compute, if I want to know the total amount, I would like to compute the area of all these bluish vertical bars. Now you see that this area is almost the same as the area below this line, which smoothly connects the heights of these bars. So if I know this line, or in other words, if I know an expression for the amount of euros C that I get each day T, what I can do is I can compute the total area below this line, and that will be a good approximation to the sum of all these little blue bars. I'm sort of missing out these little white triangles, but as these bars get smaller and smaller in size, second by second rather than day by day, you can imagine that these little white triangles that are missing here, or that I'm overcounting actually, are actually vanishing, are going to be vanishingly small compared to what I'm getting. So the area below this graph is more or less the same as the sum of all these bars, and particularly as all these bars get very small in width, this area is going to be the same thing. So this area, how can we measure the area below a graph? Well, that's why we introduce these definite integrals, right? So the definite integral below this line, this black line, that's precisely the area below that black line. So if we're interested in this total amount, we can do a fairly good approximation, measure this or compute this as the integral of our function C of t, our cash flow function, over time. So that's the idea. So as long as these cash flows occur fairly often compared to the total length of time that we're interested in, computing this thing as this area, if you wish, all the blue bars, as an integral of all the area below the black line, which measures the height of this function, is going to be a very good approximation to what we want to know. So that's what we're going to do. So we want to compute this integral, except of course in finance we're not that much interested in the total sum of money itself, but we like to look much more at the present value of these flows of money. So again, what were these present values? So if you have a cash flow at some day t somewhere in the future, the present value of that cash flow will be cash flow itself, but discounted, right? So this is the discount rate. So if the interest rate is here, this r with this twiddle on top of it, so that's the interest rate, if you wish. What we do to get the present value of this particular cash flow in, say, 30 days, when t equals 30, we take this cash flow that we get in that day, c, divided by 1 plus this tilde r to the power 30, if r is the daily interest rate. And if you have multiple cash flows, so what we want to do is we want to add up these discounted cash flows, right? The value is the sum of the discounted cash flows, each discounted with their own discount factor. So the first one here with time 1, so the first day in which we get our cash flow. The second one with t2. The second day exponent is t2, so the second day in which we get this cash flow, etc. Now, as I just explained to you, we would like to sort of, if you have lots and lots of terms, we would like to replace this sum of terms with an integral, because it makes life computationally much easier, allows us to do to get further with, in particular, with the derivative pricing. So we are interested in a continuous stream of cash flows, and it's going to be the limit in which we get our cash flow every second, perhaps even every millisecond. We are sort of adjusting our trades if we are a modern trader. What our total present value would be, adding all those little areas up, would be the same as taking the definite integral of of the present value of each of these cash flows. So C at that particular moment t discounted with discount factor 1 plus r tilde to the power t. And the adding up means taking the integral between the beginning time and the ending time. So say from today, time equals 0, to 10 years from now, time equals, well, lots and lots of seconds. And integrating over time dt. Again, this integral is then the sum of, it's very close to, or will ultimately be equal to, the sum of all these cash flows flowing each instant and discounted with each one its appropriate discount factor, 1 plus r to the power t. And be careful, we are integrating here over the integration variable t, right? So t, which occurs over here and also occurs here in this discount factor, this is a function of t, of time, and we're integrating over time here. So this is an expression. So it's also a definite integral. Question: can we evaluate this definite integral? Well, it depends on what c of t is, of course. So we just call this sum function. So we want to know, well, what function actually of cash flows do we actually have in mind? So what's the value, for instance, of a constant flow? So if cash flow is the same every second, it's the same, it's level at c, but we're discounting with this discount factor, which is evolving, right? It's getting lower and lower as t increases and increases. So if we have a constant c divided by 1 plus r tilde to the power t, can we evaluate that integral? Yeah, we can, in the sense that we know how to compute indefinite integrals of some function a to the power t. We did this, and I remarked that sometimes or often actually, it's easier to convert this into a straightforward natural exponential, and that's what we're going to do here as well. So what I would like to do is I want to simplify this 1 plus r to the power t in the denominator, so 1 divided by 1 plus r to the power t, I want to simplify this by defining a new interest rate actually, which is related to the old interest rate like this. So I call this thing e to the power minus r. That's basically um, the way that people operate in continuous time finance. We're interested in e to the minus r as our discount rate instead of 1 divided by 1 plus r. So define this new r, which will be called the continuous compounding interest rate. So you remember, compounding means I'm getting this interest upon interest upon interest, while here we are compounding continuously, hence this term continuous compounding. So what is 1 divided by 1 plus r to the power t? Well, it's then e to the minus r to the power t, or in other words, e to the power minus rt. So my discount factor, I prefer to write this as e to the power minus rt because that makes life a bit easier. So typically in continuous time finance, we use as a discount factor e to the minus rt instead of this left-hand factor. So we use the continuous compounding interest rate rather than the daily or second by second compounding or annual compounding rate rt. Okay. So let's have a look. So if I rephrase this in terms of this new discount rate with the continuous time continuous compounding, then we want to evaluate, well, this constant cash flow C discounted by this discount factor, e to the power minus r to the power t, or e to the power minus rt. And I'm going to evaluate this between the initial time 0 and the end time capital T, which might be far into the future, years from now perhaps. So this is the total value. This is the total present value, I should say, of this stream of income between 0 and 10 years from now, capital T from now, discounted. Can I evaluate this? Yes, of course. This is just a definite integral. So we're asking, can I compute this definite integral? So it's here, and but I'll do it for you on paper anyway. So here we go to paper. So I'm asking now, can we compute the integral, the value v, the definite integral between time goes from 0 to capital T. The function that I'm integrating is e to the power minus rt times some constant c. I'm integrating over this little t, the time. Interpretation of this is time. But yeah, now this has been turned into just a mathematical problem, right? This is a function of little t. I'm integrating over little t, and little t runs from the beginning time, 0, t equals 0, to the end time, t equals capital T. Can I do this? Sure. So what do I need to do? I need to evaluate between these two boundaries, t equals 0 and t equals capital T, the indefinite integral of this expression. So what is that indefinite integral? Is going to be c times e to the minus rt itself. So what happens if I take the derivative here? Well, then this minus r will come down, right, by the chain rule. I don't want that because this is precisely what I need. So I have to divide by that. So I multiply this by 1 minus 1 divided by r. So this, by making this, using this expression for the indefinite integral, I make sure that if I take the derivative of that thing, indeed gives me the function that I'm after. Now I have to, well, that's the indefinite integral. I have to compute the definite integral. I have to evaluate this first at the upper boundary. So I have to substitute for every little t, well, it's only here, the capital T, and now to subtract the same thing, but now evaluate it at little t equals 0. So how much is that? It is minus 1 over r equal to c, put it here, e to the power minus r, well, big T inserted, minus c over r e to the power minus r times 0. That's just 1, right? E to the power 0 or e to the power minus 0 is just 1, so times 1. So how much is that? Brackets around this just to make things clear. So this first bit is the indefinite integral evaluated at capital T. The second bit is the indefinite integral evaluated at little t equals 0. And I'm subtracting that from the first bit. So how much is that? It's the minus times the minus gives a plus. So let me first take this thing then. Let me C over R from the second term here. And then I have this minus over here, minus C over R. And this is the same thing, of course. And if I want to write this in a little bit more nifty way, I will just do this. Take the C over R out of the brackets to get me this expression. So there we are. Now this thing actually has a name, and the name that we use in finance for such a cash flow that occurs constantly over time between some fixed initial time 0 and some fixed end time capital T, constant cash flow, it's called an annuity. So this is actually the annuity formula that you know from your finance courses, but in its discrete time form. So particularly, we might also be interested in what is the perpetuity value. What's a perpetuity again? So if you remember your finance courses, or if you're having your finance courses now perhaps, a perpetuity is just an annuity, so a fixed cash flow, but not occurring until some fixed time capital T, but occurring forever. So the perpetuity, so this was an annuity. The perpetuity, the value of a perpetuity is the same integral, but now where the end time is actually infinite. So you forever have the cash flow C. Well, by looking at this expression here, we have precisely the same computations to make here, so we'll get the same answer, except that we need to take, well, formally we need to take the limit of this capital T becoming very, very, very big. That's what this infinity basically means. It means the limit of taking this n time t as big as you like. Well, what happens? Well, where's this capital T occurring? Only here, right? So what happens if I take this t to be huge? Well, e to the power minus r times something huge is going to be 0, right? This e to the power minus a very large number. It's a very, very small number. So the larger I take capital T, the lower this second bit here gets. So ultimately it gets, in the limit, it gets 0. So the result is this thing is going to be 0. So we get CR times 1 minus 0, or in other words, just C over R. So this is the perpetuity formula. If you get the perpetuity of a constant C euros per unit of time, what's the total value of that? If you get this indefinitely until infinity, its value is C over R. And you might actually recognize this also from your discrete time finance course if you have seen that. So this is the perpetuity formula. So let's get back to the slide. So again, here we were computing this this annuity, right, between 0 and capital T. We had to take the definite integral of the function of little t e to the power minus rt times the constant cash flow. How did we do that? By writing down the indefinite integral and then evaluating that, well, first at little t is capital T, the end time, and then at little t equals 0, and subtracting those two then give the second one from the first one gives us this final expression for the annuity formula. And then as we take this t to infinity, so make it larger and larger, you see that this term is getting smaller and smaller and smaller until it's 0, and the perpetuity formula accordingly is C over R. And you can of course do similar computation where C is not constant, but it might depend on time. So second application, let's have a look at probability. So probability of course is important, particularly in econometrics parts of economics and of finance as well. And you know, of course, if you have seen a little bit of econometrics, that there's one distribution, probability distribution, which plays a huge role, and that's the standard normal distribution, right? So perhaps you know some things about the standard normal distribution already. So it's perhaps you remember it's represented by this particular bell curve, and perhaps you also remember that it measures the mean, the average of the standard normal as 0. And this bell curve basically measures the amount of probability for the various outcomes if you make a draw from a standard normal distribution. In particular, you might know that, for instance, taking a draw between one standard deviation below the mean and one standard deviation above the mean, the total probability of getting such a draw is approximately 68%. And similarly, for getting 2 standard deviation around the mean, the probability of getting a value there if you make a draw from the standard normal distribution is about 95%. And these percentages are actually, these probabilities are actually therefore associated to the area under this curve. So these numbers here are actually the areas under this curve. So that's where area ties in with probability. So area under a probability distribution actually means the total probability of having some event occurring in that range, for instance, between -1 and +1. So what does this standard normal distribution actually look like? Well, it has a density, and this density is this particular function. So you might have seen this. There's a number here, 1 divided by the square root of 2 pi, where of course pi is this famous 3.1415, etc. So this is just a number, times e to the power minus x squared over 2. So if you plot this function, we'll get exactly this purple graph here. So you see that as x gets either very big or very small, you get e to the power minus something big. So it goes to 0, and it's highest actually when x equals 0, which corresponds to basically the middle here of this graph, where this function reaches its highest point. So indeed, we can indeed compute the area between -1 standard deviation, because the standard deviation of the standard normal distribution is 1. So 1 standard deviation around the mean, so around 0, will give us, can be computed as the integral between -1, the probability of ending up there is the integral between -1 and +1 of this distribution. The area under the graph between -1 and x equals -1 and x equals +1. So how do we calculate an area? Well, by doing the definite integral. So the definite integral indeed ends up being this 68%, 0.68. Similarly, the area under the entire graph, well, the probabilistic meaning is the probability of making some draw, whichever number you get, that needs to be 100% or 1, right? So something happens with probability 1. So the total integral under the standard normal density, that's going to be 1. Yeah, this is not very easy to verify, so you just can take it from me at this point. So you can of course prove this as well. But let me know that this particular function does not have an indefinite integral which we can write in terms of the elementary functions that we have looked at so far. So you have to introduce a new function actually which you'll use to define this area. We'll not do that here. But take it from me, if you evaluate this integral under the whole function, it will over the whole domain between -infinity and +infinity, you will get exactly 1, as you should. So we can also look at what's the expected value. So in general, if we have some distribution function, so like this standard normal distribution function, so the f of x that we just had, what's the expected value of any number that we draw from that distribution function? Where the integral is defined as the integral over the whole domain, so in this case between minus infinity and plus infinity, of x times the density, integrated over x. So let's do that indeed for the standard normal distribution. So let me do that on paper again. So I mentioned the expected value of some variable x, which is distributed according to some distribution function, distribution density. That's given by the expected value of x, or the average if you wish, the mean value of x, is the integral over the whole domain. Let's just assume here this whole domain is, for this case, minus infinity to plus infinity, of x times the density. Put brackets for clarity here. So I'm looking at the integration of the function x times density f of x. So for our standard normal distribution, I told you that the density function for the standard normal was this square root over 2 pi times this exponential e to the minus x squared over 2. So the question is, can we indeed compute the expected value if we use as our density function this particular function f of x? Well, let's try this. So standard normal, right? Standard normal. So the expected value, the average value, the mean of x, is going to be defined as the integral of x times this thing. So let me write it as, take that 1 over 2 pi over here, x times e to the power minus x squared over 2. I'm integrating this over the x. Can I evaluate this integral? So this is just a constant. I don't need to worry about this. I could even put it in front of the integral. But can I somehow integrate this new function that we have here, x times e to the power minus x squared over 2? Is there some function that if I take the derivative of it, I get x times e to the power minus x squared over 2? And the answer is, yeah, there is actually, and we can see it perhaps by, let's wonder what's actually the dx of e to the power minus x squared over 2 itself. How much is that? Well, we have to use the chain rule, right? So I have to take the derivative of what's up here, the interior function. What was the derivative of minus x squared over 2? It's actually minus 2 over 2x if you wish. So the 2 is coming down, it's going to cancel against this 2, and the x squared becomes the x, and I have to multiply this by the derivative of the exterior function, which here is the exponential function, but that's the exponential function again itself. So we get here minus x squared over 2, or in other words, this is minus x e to the power minus x squared over 2. But look, that's exactly what we wanted, right? Well, almost. We wanted this thing, we got the same thing, but with a minus sign. So what's the integral of this object here? Well, it must be minus the object over here. So minus this object, if I take the ddx of that, the derivative, would get me exactly the encircled bit here. So this is going to be, let me just take the 1 over 2 pi over here. I'm going to, this is just a straight line, I'm going to evaluate between minus infinity and plus infinity the indefinite integral, which is minus minus e to the power minus x squared over 2. Because if I take the integral, I'll write it explicitly here, minus e to the minus x squared over 2, that's going to be x times e to the power, which is precisely what we need. Right? So this is the indefinite integral. How much is this? 1 over square root of 2 pi times minus e to the power minus, well, plug in infinity, well, e to the power minus infinity, right? So infinity squared, that's a huge number. So e to the power minus infinity, that limit is actually 0, so it's minus 0. Similarly, if I plug in x equals minus infinity, well then still x squared is still going to be infinity, right? Minus times minus is going to be plus 1. So it's again going to be e to the power minus infinity. So again, that's 0 as well. So plus 0. So this is exactly 0. So the outcome of this integration is 0. Or in other words, this integration, what was it? It was the expected value of x. The average value, the mean value of x, is going to be 0 for the standard normal. Precisely what you already knew, of course, but this verifies that. And the same computation is down here. So this was the standard normal distribution. Of course, there's many other distributions. So one other one which you do encounter in real life, I might also, at least in economics, a lot, is the uniform distribution. So a uniform distribution is not this bell curve, it is rather just a random number between 0 and 1. So if I ask you to pick, or if I ask the computer perhaps to pick a random number between 0 and 1 where each number is equally likely, I would pick this according to the uniform distribution. So what's the probability density? Well, everything's equally likely, so this density must be equally high everywhere. So the density is just a constant. So this is the density function for the uniform distribution. So it's unlike this bell curve, which was a standard normal distribution. For the uniform distribution, the distribution is 0 outside the interval 0 and 1. There's no probability that you get a number outside of 0 and 1, this interval, but any number between 0 and 1 equally likely. So again, well, let's have a look here. What happens if we want to consider the probability that we take any number between, well, between some a and some b, both between 0 and 1? Well, that's the area under this curve, right? The area under this blue line, essentially, between the numbers a, which might be here, and the number b, which might, for instance, be here. That area is just, again, the definite integral. So can we take the definite integral of the number 1? Yeah, we can integrate the number 1, right? So its indefinite integral is x, right? Because the derivative of x is just 1. So I have to evaluate the function x at the upper boundary, b, gives me b, minus the function x evaluated at a, so minus a. So the probability that I take any number between a and b is just b minus a. The particular probability that I find any number between 1 and 0 is going to be 1, because all the numbers that I pick will be between 0 and 1. Whereas the probability that I take a number which is, say, below a half, but above 0 will be a half minus 0, or in other words, a half. So half of all the draws that I'll make will be a number below half. And of course, the other half will be the numbers above a half. So we can also look at the mean of this uniform distribution. I can guess where the mean is, I hope. So if you take any number between 0 and 1, well, on average we'll get the number, the mean, if we make many draws, I should say, should be a half. Let's check whether that's the case. Well, what again was the expected value? I have to take the definite integral of the area under the curve between 0 and 1 of the whole domain, which in this case is only between 0 and 1, of x times this density, which was 1 for our particular case, so x times 1. Can we integrate x times 1, or in other words, x? Well, we know what the indefinite integral of x is, right? It was a half x squared. So the indefinite integral is a half x squared. We have to evaluate that at the upper boundary, subtract the lower, the same thing, evaluate at the lower boundary. So if I plug that in, so 1 squared, that's 1. So 1 divided by 2, the upper boundary, we get a half. the lower boundary. So if I plug in 0, I get 0. So a half minus 0, that's exactly a half. So indeed, the average or the mean of this uniform distribution is precisely a half as we would like it. And you can check for yourself that the variance, which is defined in this way, the expected value of x squared. So instead of plugging in x here, we would have to plug in x squared here. You have to integrate x squared between 0 and 1. And for variance, you have to subtract the square of the mean. And if you do this, you might be able to convince yourself that the outcome will be 1/12. So do this at home. That's probability distributions. The third application is about a microeconomic example, which is about consumer and producer surplus. So you see here the typical microeconomics graph of supply and demand. So you see a downward sloping demand line, which is the black line, which is downward sloping here. It's given by a function here, P equals F of Q. So it depends on Q. It's downward sloping because the more quantity there is, the lower the price will be. And on the other hand, the supply function, which will typically be something like the marginal cost, for instance, of the firm, so there's a competitive equilibrium, is this upward sloping line, which is here in general called G of Q. So if you have a market with demand F of Q, P equals F of Q, and supply measured as P equals G of Q, like we have here. So what's the equilibrium going to be? Well, equilibrium is that quantity at which supply equals demand. So what does it mean? Supply equals demand. F of Q will be the same as G of Q. This will give rise to some quantity Q star over here. So when these two lines cross, it's the quantity Q star. And that occurs at a particular price. That's the equilibrium price, and that's called here P star. So now we can get to surplus. So surplus is basically a measure of total welfare, if you wish, of welfare, and also how it's distributed. So in particular, we consider and distinguish here the consumer surplus, so the welfare for consumers, if you wish. That's measured, as you know from your microeconomics course, as the area under the demand curve, or in between the demand curve, I should say, and the price. It's the red area over here. And similarly, producer surplus, which you might say is profits for firms, essentially, is the green area here. It's the area below the price, but above the marginal cost level, which was this supply function line. So the green area is known in microeconomics as the producer surplus, and the total surplus is just the sum of these two. So the question now is, how can we compute, if we know what this demand function F of Q is, and we know what the supply function G of Q is, can we somehow, well, first of all, compute what the equilibrium is, so what's Q star and what's P star, but in particular, once we know that, can we compute the red area and the green area, the consumer surplus and the producer surplus. So let's have a look first at the consumer surplus. So again, what's consumer surplus again? It's the area below the demand curve, so below this function F of Q, but above the line P star. Well, we know how to compute areas below a curve, right? But we know by saying the area below a curve, we mean the entire area below a curve. So you would know how to compute this area A, because this area A is just going to be the area below the demand curve F of Q between the boundaries 0, Q equals 0, and Q equals the equilibrium quantity Q star. So you can compute A, but then we have too much, right? That's more than consumer surplus. So we have to subtract something from that, the area that we overcounted, which is basically this rectangle, this white rectangle below, which is denoted by B. So how large is this area B? Well, it's actually the area below the equilibrium price, P star, between 0, Q equals 0, and Q equals the equilibrium quantity Q star. So the total consumer surplus is just this area A, the total area, minus this bit, this rectangle that we overcounted, minus the area B. Again, what's the area A? Well, area was the definite integral, so the definite integral of the demand under the demand curve, F of Q, evaluated between Q equals 0, left-hand boundary, and Q equals Q star, the equilibrium quantity on the right hand side, minus area B, which is the area below the constant price of P star, is a constant equilibrium price. Again area, so again have to take the interval between 0 and Q star of this constant P star, integrated over Q. In other words, we can of course combine these two terms into one integral between 0 and Q star, Q equals 0 ranging until Q equals Q star, the equilibrium quantity of FQ minus this equilibrium price P star, integrated over Q. So that's what we need to do to compute the consumer surplus. Same way basically to compute the producer surplus. So what was that again? So it was the area between the price and the supply function, marginal cost function for instance. So what is that? So price is a P star again, so it's again a constant. So what is this green area? It's actually the difference again of the total area under the price. There's a whole rectangle here, but then we have overcounted because this white area is too much. So you have to subtract the area under the supply curve, or the area D here. So the first one will be this first area C, the interval of P star between 0 and Q star, and we have to subtract the area D, which is the integral under the supply function G of Q between those two boundaries C and Q star. And again, we can combine those two into one integration. So here you see indeed again, consumer surplus and producer surplus again are two areas. So and indeed we can compute them as two definite integrals. So let's do that for an example. So here we have an example for a given demand function f of q. Well, what is it? This particular demand function is defined to be 6,000 divided by q plus 50. So it's a downward sloping function. Yes, you might be able to check, but it slopes down in lower and lower at a lower and lower slope. And similarly, we have a supply function, which is actually just linear, so it's easier actually. The supply function, so this upward sloping curve, is just a linear function q plus 10. So let's see whether we can compute the consumer and the producer surplus. So in order to do that, we would first have to solve for the equilibrium quantity q star and the equilibrium price p star. So let's do that, and it's done over here. But for you, I'm going to do it on paper again. So we have demand, f of q equals 6,000 divided by q plus 50, and we have supply g of q equals q plus 10. So first we want to know what's the equilibrium. Well, that occurs where f of the equilibrium quantity needs to be, demand should be equal to supply. Or in other words, let's just plug that in. 6,000 divided by q star plus 50 should be equal to q star plus 10 supply. So let's try to solve this. We need to know what q star is. If you know q star, we can also compute what p star is. So let's solve this. Do that here. So we see q star is of course going to be a positive, 0 or positive number. So I can actually multiply without any problem. I can multiply with q star plus 50. It's always going to be a positive number. So let's do that. So I get multiplying the left hand side with q star plus 50 gives me 6,000. And the right hand side gives me q star plus 50 times q star plus 10. Let me just get rid of those brackets immediately. Gives me q star squared, those two, plus 50 q star plus 10 q star, so it gives me plus 60 q star. plus this quadratic 50 times 10, so plus 500. So 6000 is this quadratic expression here. Can we solve that for Q star? Yeah, of course we can. So let me write this as Q star squared plus 60 Q star plus 500 minus 6000, that's minus 5500 equals 0. Well, do you see the answers here? Well, if you don't, use the ABC formula, right? That will always guaranteed work if there is a solution. Otherwise, you'll find there cannot be a solution. But sometimes you can actually see already what the solution is, and this might be one of such cases if you have a closer look. So can we find two numbers which upon multiplication gives us minus 5500, and if I add them up, it should give 60, and the answer, if you think a bit, so think about this for a bit, pause the video. Okay, now you've thought about this, so perhaps you have found that indeed we can write this as Q star plus 110 times Q star minus 50, because 110 minus 50 gives us need 60, and 110 times minus 50 gives me the 5500. So what's the answer for Q star? Well, there's two answers, right? But one's going to be negative. So Q star is minus 110 will do the job, but we cannot have negative quantities that we can produce. So the only relevant answer comes from this term being 0. So Q star equals 50. Q star equals 50. That's the equilibrium quantity. So then what's the equilibrium price? Well, we should be able to find that either from plugging in this number in the demand function or in the supply function. And actually they should both give the same answer. So let's see whether that's true. So from the demand function, P star would be 6000 divided by Q star is 50. 50 plus 50 or 100. So 6000 divided by 100, that's 60. And from the supply, let's verify whether that's the same. It should of course be 50 plus 10 equals 60. So this is reassuring, and we didn't make any computational error here. So we now know the equilibrium for this particular demand function and supply function. So the equilibrium quantity will be Q star equals 50. The equilibrium price will be 60. P star equals 60. So now we can head on, so we know how to proceed. So let me go to the next page. So we had, let me just reiterate what we had. So we had the demand function was 6000 divided by Q plus 50, and the supply function was Q plus 10. So we now know that Q star, the equilibrium supply, was 50, and P star, the equilibrium price, was 60. So now we are interested in computing the consumer surplus. So what was that again? Well, consumer surplus was this area, right? The area below, so here we have P star, so 60. Here we have Q star, 50. Here we have this function, f of q. And C star is this, more or less triangle, if you wish, not exactly a triangle. So we want to compute this particular triangle. What is it? Well, it's the integral, so we wrote it as this difference between the total area under this graph, between Q going from 0 to Q star, which is 50, of f of Q, I'll just plug it in, 6000 divided by Q plus 50, minus the price, because we don't want to count this white rectangle here. So minus 60, and we are integrating this over dq. So now we can look with our mathematical eyes here. This is just a definite integral that we want to compute. So how do we compute a definite integral? Well, we need to evaluate between these two boundaries, 50 and 0, the indefinite integral of this bit. So can we compute that? Well, the first bit, we have 1 divided by q plus 50. And a little bit of thought perhaps teaches us that, well, this will be the logarithm of q plus 50. If I take the derivative of this logarithm of q plus 50, the answer will be 1 divided by q plus 50. I still need to multiply, of course, by this 6,000. So that's the first bit. So this first bit is the indefinite integral of the first term over here. Second term is easier, of course. So what function gives me the number 60 if I take the derivative? Well, that's of course the function 60 times q. If I take the derivative of 60 times q, that will be just 60, just what we need. So this is the indefinite integral, and we need to evaluate that first at 50, q equals 50, and then at q equals 0, and then subtract those two. So let's do that. First bit, 6,000 times the log of 50 plus 50, that's 100, log of 100. Let me then immediately subtract the same thing with q equals 0. It will give me log of 0 plus 50, or in other words, log of 50. And for this one I get minus 60 times 50, that's minus 3000, I guess. 5 times 6 is 30, times 10 is 3000. Minus, now q, plug in 0 here, gives it 0. So let's stay out. And now we're of course almost there. So now you note, well, this 6,000 times a log, you take the 6,000 out of the brackets, a log of 100 minus a log of 50 minus 3,000. For clarity, I'll put some brackets in here. Now you might remember that the difference of two logs is actually the quotient of those numbers, of the log of the quotient. So this thing which here, this log of 100 minus the log of a 50 is actually the same thing as the log of 100 divided by 50 times 3,000. And finally, the log of 100 divided by 50 is of course the log of 2 minus 1,000. So this is the final answer. So this is the consumer surplus. What's a producer surplus? Well, same thing. So producer surplus, I have this linear function, right? So producer is supply function is this increasing line. We're interested in, this is P star, or 60 actually. Equilibrium price, again here is Q star equals 50. And we are now interested in this area here, which is the producer surplus, which you can compute as, again, the definite integral between q equals 0 to q equals 50 of, well, the price, 60, upper line, minus the lower line, so minus the g function, q plus 50 is the function g of q, this function. And I'm again evaluating that integral between 0 and 50. So again, this is just mathematically speaking some definite integral, an easier one even, which you can therefore compute. So what is it? Well, let me first get rid of those brackets in here. So it's just 60 minus 50, that's going to be 10. And minus q is minus q. Q. Oh, sorry, I'm doing something. I wrote here Q plus 50, but that's of course not true. The GQ was actually Q plus 10, right? That was the definition of the supply function, so there should be a 10 here. So if 60 minus 10, that should be 50. 50 minus Q. So this is the function that I need to evaluate. 50 minus Q, I need to integrate that for Q going from 0 to 50. So what is that? Well, what's the indefinite integral of 50 minus Q? Indefinite integral of 50 is 50 times Q. The indefinite integral of minus Q is minus a half Q squared. And I need to evaluate this, the upper boundary, and then subtract from that the same thing evaluated at the lower boundary. And that is 50 times 50 here. That's 2500. Minus a half times Q squared, minus a half times 2500, minus 1250. And when I plug in Q equals 0, both these terms are going to vanish. So this is it. So of course 2500 minus 1250 is exactly 1250. So producer surplus for this case is precisely 1250. So let's go back. So here is again this computation of the equilibrium quantity and prices. Q star was 50 and P star was need 60. And here are these integrals that we just computed. So these two expressions should now look familiar. So this is the end basically where we want to get at. So if you look at three applications of why are we interested actually in areas below graphs. So we looked at this continuous time finance case where we want to integrate present values of cash flows typically. We looked at integration under probability distributions which might occur in your econometrics courses. And we looked at a final thing in this microeconomics application of consumer and producer surplus, which are again areas below demand and supply curves. So that said, that's all we want to do about integration in this course. So next time we'll have a look at the 7th lecture at matrices. See you then.